Hello, everybody. Today we will be solving problem 2 of the 2019 JMO. The problem reads, let Z be the set of all integers. Find all pairs of integers a comma b for which there exist functions f from z to z and g from z to z, satisfying f of g of x equals x plus a and g of f of x equals x plus b for all integers x. Okay, so before I go and do any math, I'm actually just going to take g of this whole equation. I'm going to take g of both sides. And I'm going to get g of f of g of x equals g of x plus a. And then I'm going to let g of x equals to, I don't know, p for some number p. And at this point, I'm going to get g of f of p is going to be equal to g of x plus a. But hey, wait, g of f of p from this equation over here is p plus b. And I can write this as g of x plus b. And now we have this equality, g of x plus a equals to g of x plus b. Okay, now we're going to do the same thing with the other equation. F of this equation over here, f of g of f of x equals f of x plus b, right? But then we realize that if we plug f of x into the argument of this equation, we get f of x plus a. And I should really write this as g of x plus b. Right? So we have this first equation, we have this second equation. And what's that going to mean? It's going to mean if we just take a look at f of x here, and we take a given x, let's call it for some x equals k, we get, if we take f of k, and then we increment this k by b, we're going to get f of k plus b is going to be equal to f of k plus a. And then for x equals k plus 2b, well, f of k plus b is going to be equal to f of k plus b plus a. So this is going to be equal to f of k plus 2a. And essentially, for the function f, every time you increment x by b, you're going to increment f of x by a. So sort of like a line, but not quite like a line. And the reason we can't just assume it's a line is because if you have this coordinate plane and then you draw out some integer values of x. And for the moment, let's assume a equals b equals 2. We could very well have f of 0 equals 0, then f of 1 equals -1. Then f of 2 would be f of 0 plus 2. Then f of 3 would be f of 1 plus 2. And f of 4 would be f of 4 would be f of 2 plus 2. And the graph looks something like this, and we can see that this is clearly not a line, right? So that's why we can't just assume it's a line, although it does act kind of like a line, right? And the same with g of x. G of x, every time we increment x by a, g of x is going to increment by b. And the claim that I want to prove here in this problem is that the absolute value of a is going to be equal to the absolute value of b. I claim that those are the only pairs of A, B that work. And the reason is, first we consider the case where one of them is 0. So without loss of generality, we let A equal 0. Then we get from this equation over here, g of x plus 0, that's just g of x, equals g of x plus b. Right, and then we can subtract g of x from both sides and we just get b equals 0. So if a equals 0, b equals 0, and vice versa, if b equals 0, that's enough to imply a equals 0 for a similar reason. So from now on, we assume a and b are not 0. Okay, now we're gonna assume for the sake of contradiction. We're gonna assume for the sake of contradiction that the absolute value of A is not equal to the absolute value of B. And so without loss of generality, we let the absolute value of A be less than the absolute value of B. Okay. Now what we're gonna do is we're actually gonna take this equation over here, mod absolute value of B. Right, and the reason we can do this is just since B is non-zero. And we get g of x plus a is congruent to g of x mod the absolute value of b. Okay. So g of x is equivalent to g of x plus a, which is equivalent to g of x plus 2a. So like, for instance, g of 0 is equivalent to g of a, which is equivalent to g of 2a, which is equivalent to g of 3a, and so on. Similarly, g of 1 is equivalent to g of a plus 1, which is equivalent to g of 2a plus 1, and so on. And then we can note the same for every x between 0 and a minus 1. And note that we can also say things like this is equivalent to g of negative a and stuff. So eventually we end up with g of a minus 1 is the equivalent to g of 2a minus 1, and so on. Which means this function g of x, in the range of g of x, there will only be a residues mod absolute value of b. There will only be absolute value of a, should I say, residues of absolute value of b, mod absolute value of b. And the reason is because since the domain of g is integers, right? So that's 0, 1, 2, 3, and so on. And then we take g of each of those integers, and each one of them is going to fall into one of these equivalence classes. They don't necessarily have to be distinct, right? So there would be at most absolute value of a equivalence classes mod absolute value of b. And note that since the absolute value of a is less than the absolute value of b, there will be equivalence classes that are not represented. So there exist integers not in the range of g. Or I can also write this as there exist equivalence classes. Okay, now we just need to search for contradiction. Meaning, and the way I'm going to do this is I'm going to say, okay, I'm going to prove that every equivalence class is accounted for in the range of G. And the way I'm going to do that is I'm going to prove that G is surjective. And what does that mean? It means that you can get every single integer out of G after applying G. Right? And that's easy because this thing is going to be a different integer for every value of x, right? Because x plus b is just a straight line. And that is surjective. And since this is g of some number, essentially this number is in the range of g for all x. So that would mean g is surjective. But that would contradict this statement that there exist equivalence classes not in the range of G. So absolute value of A not equal to the absolute value of B cannot be true, right? So now we've narrowed our solution set down to absolute value of A is equal to absolute value of B. Now we just need to prove that this is true for all absolute value of A is equal to absolute value of B. And we can just split this into two cases, one where A equals B and one where A equals negative B. And if A equals B, then we get G of x plus A is equal to G of x plus A. So we just have G of x is equal to x. And similarly, f of x is equal to x. And then if A is equal to negative B, then we can just take G of x is equal to negative x. And then f of x is equal to negative x as well. You can verify for yourself that those two functions work. So essentially, we've just proven this claim where absolute value of A is equal to absolute value of B. And we are done. Thanks for watching, and I will see you next time.